All right, welcome back again, folks. What we need to do now is to formalize some of this stuff that we've been doing with motion. We've been looking at things we're kind of comfortable with because we're used to driving down the highway and all that kind of stuff. But we need to kind of spruce this stuff up a little bit to make it more powerful. That are things that are come ahead. And so let's go ahead and first of all look at the enemies in the eye and see what you're up against. This is a little gadget here that I'll be using some today. This is a deal about the equations you're supposed to know about. You don't need to worry with all those details right there because most of them don't apply to you. But this bottom box down here on the right exactly matches what you see on your homework, or pretty close to matches what's on your homework. And these are the 5 kinematics equations. And as it says on the homework there, it says that you need to memorize these 5 equations by test time. And that's the test over chapter 2. And I would recommend that you try to hurry that up a little bit so that you can be real comfortable with it. Now, these equations, I'm having you memorize these right away on the first test because they're used throughout the course. They're probably the most important equations that we use. So they're used a lot. You need to just have them all ready to go whenever you need them. Some of the other things that we'll be dealing with, we'll have equations where they aren't so important that you need to stash them in your brain with all the rest of the stuff. And so I'll have those equations at the top of your tests and everything, and I'll let you know. For example, on the homework, if it's an equation that you need to know how to use but don't have to have memorized, I'll make a note of that, just like on this homework I've done otherwise. So anyway, those 5 equations there are what we need to talk about today. And on your homework, you'll see that I've written 2 different ways in 2 different columns, and the right-hand column corresponds pretty well to what's in this column right here. So anyway, that's those guys there, and let's get rid of them. Okay, what I want to do is I want to try to approach this stuff by looking at a piece of apparatus that you're getting ready to use shortly after this section. Actually, right after this section, you're going to do a lab where you're looking at graphing velocity versus time. And so this is the apparatus you're going to work with. It's called a dynamics track. You can buy the real thing for a couple of $1,000. That would include the computer. So anyway, we have our own that you don't have to pay for here. And there it is. We have a cart that's bouncing around there. And let me just calm it down a little bit. Okay, so it acts exactly like you would think it would do if it's on a frictionless surface. And it has other good things you can do to it. For example, you can attach a string to it and hang a weight onto it over there and see what effect that might have. And it has rocket engines and all kinds of other stuff, but we're going to reset all and get it back to where it was because we're just going to look at a nice lazy horizontal track here. Okay, what I want to do here is I want to get this thing started. I'm going to click go here. And what I'd like to ask you, and please feel free to pause me in an embarrassing position, to think about this. How fast is this cart going? How are you supposed to know? Well, there's a big screen full of stuff here. Have a look at it. Hopefully you'll notice that right next to that go button, there's a VO thing. That's the original velocity. This originals and finals are something very big to us, and those equations had the F's in them and some of them had the O's in them. But anyway, this is the original velocity. When I fired it, it takes off at that velocity, and it's 40 centimeters per second. Okay, now, this is, in this case, other than the fact it's kind of jerky there, this is its constant velocity, or excuse me, its constant speed. It's changing direction, so it's not a constant velocity. The velocity includes direction, as we'll talk more about in a moment here, but it has a constant speed of 40 centimeters per second. Now I'm going to make a little, well, as a matter of fact, let's look at the graph here first before I go on and do that. So I'm going to get this thing going, and I'm going to click this little sensor deal, and suddenly a graph appears. Okay, let's turn that thing off and see what's going on here. First of all, there's a little sensor. It's an ultrasonic sensor. It sends out imaginary for us sound waves that are outside of our hearing range, and those waves bounce off the cart and bounce back, and it uses the speed of sound and the time delay to figure out where the cart is at every instant. And the real version of this apparatus works just like that. That's actually very much what it looks like, and that's how it works. And it is not quite as foolproof as ours is, but actually it does a really good job of it. So that's the sonic deal. Now, what's going on with this graph? Let's look at what we're plotting. We have time along the horizontal axis, and we have position. That's a kind of new term for us here. We haven't talked about the position. We've talked about distances, but the position is just a measure, and let me just turn on a ruler here. It's a measure of where actually the mast of the cart is on this track. So if I turn on the sensor right now, you'll see a constant horizontal line at 20 centimeters, because there's 1 meter, there's 20 centimeters. It's staying constantly at 20 centimeters. Okay, so that's the position versus the time that we're looking at there. Okay, now let me get back to what I was doing there, and I'm going to turn on the sensor and get it going. Alrighty, now we know that the speed is 40 centimeters per second based on what the go thing tells you. How else could we find out how fast this thing is going? Well, this graph is telling us where its position is over time. And I'm going to do something to try to make this a little bit easier to think about. I'm going to say, suppose that we looked at its motion, say from, let's say that's 1 meter, 60 centimeters. I'm going to drag a little line down to 60 centimeters. Right about there. And I'm going to draw another line down. Let's go up to 80. So we're going to go 60 to 180. So that's 120 centimeters there. Okay. And notice what happens. I'm going to click this match graphs things to 1, and notice what happens with that little dot. Notice how the dot matches up with the position of the cart. So when the cart is right here, notice it's at 60 centimeters. Okay, just like it matches down here. And then when I get up to 120 centimeters right there, 160 centimeters, it's right there. So notice what we have here. When the cart goes between 60 and 160, 60 and 160 goes, there's a 100 centimeter span there. And so as the cart travels across there, it crosses the 60 now and the 160 over there. But notice also, if I turn this off, if I drag these little guys out to cross right there, and this little guy to cross right there, notice that we have the time when it was at 60 centimeters and the time when it was at 160 centimeter. So we have the original and final time for a little trip here and the original final position. So we can find the distance it travels and the time interval. Okay, the distance is the height between here, which is and there, which is 100 centimeters, and the time is from about 2 point something to 5 point something seconds. So it looks like it's about 5 seconds to go this distance here. Okay, so that distance over that time gives us the speed. Is that okay? All right, and let's see, we're not ready for that quite yet. Now let's go ahead a little bit further than that. We have that much of it going. Now let's try something a little bit different. And I'm going to start it going again and get it going and let it do all that plotting. But then I'm going to lower this thing down to 5. Okay. What's changed here? Well, 2 things have changed. One thing is 3 things. The cart has slowed down. How fast do you think it was going over here? Based on your vast knowledge of guessing at how things work here. Well, that recoil says recoil times VO. What that means is when it hits this end over here, it actually bounces back at half the incoming speed. Now that's not half this V over here, it's half the velocity it had, speed it had when it arrived here. So you wouldn't be surprised to find that to go through the same distance will take longer and longer and longer, or twice as long. It seems kind of obvious. If it's going half as fast, it'll take twice as long. Now, so we found that we can find these change in position and change in time here. Those two things are the slope of this graph. And when we talk about the change in position, we're actually talking about what's called the displacement. And let me see if I can find, let's go a little bit further over here to get to that stuff. Oh yeah, that's actually, I'm where I wanted to be. I was where I thought it should have been to begin with, okay? We have the position. We're going to make some definitions here. The position, which is a vector. Now, what is a vector? A vector is anything that has both a magnitude and a direction. Not just direction or not just magnitude or how much. It has both. So, for example, your weight is a vector because you weigh 142.5 pounds, okay? What's the direction of your weight? It's downward, okay? Your weight is a force. It's the force of gravity on you, whatever the heck that is, and people are still making a good living trying to figure that out. But your weight is a force that's downward, has a direction, and has a magnitude, depending on what units you use. You're 145 pounds or so many stones or whatever. Anyway, so vectors are quantities that also have directions. The speed, and I've been kind of, going back and forth with those two words there. So far, it didn't really matter which one we used. But when we start getting involved in considering the directions of things, then we're talking about vectors, and we have to be more careful. So the position of something is a vector whose magnitude and direction indicate the distance an object is relative to some arbitrary reference point. Well, in our case right here, if I move the cart all the way over there, that's at about, somewhat less than 10 centimeters. We're measuring things relative to 0 centimeters, which is right over here. The cart can't get there, but the track can get over there. So we're measuring relative to right over there. It'd be nice if I could slide all that over and have positive, 100 centimeters positive over here and minus 100 over here, but we just haven't gotten around to doing that. But it turns out it doesn't make any difference where your reference point is. If you take the final position, x final, minus the original position, you get the displacement, the change in position. Okay, so on the way over here from 60 to 160, the displacement is 160 minus 100, or 100 centimeters. Now on the way back, the final position is 60 minus the initial 160, so the displacement is minus 100 centimeters. Whoopee! Okay, why would that matter? Well, for example, we're going to be doing things like diving off a diving board, okay? You can measure your position. We'll be able to figure out things like if the board is so high and you leave the board at a certain upward velocity, we can predict how long it'll take you to hit the water, which is important if you're a diver, because divers are going 1,000, 1,000. They're keeping track of the time. When there's a tournament right now, or at least it's in the past for you, there's a tournament right now where people are, I think it's a Red Bull thing, where divers are going around the world diving off of various cliffs and railroad crossings and all this stuff right now. Those people are used to diving back home. They need to know about those heights to know how many flips they could get on the way down and all that kind of business. Okay? All right, so anyway, where was I? Okay, so we need to, when we're solving that problem with jumping off the diving board, we're going to start at a certain height. We're going to go up so much and end up down below where we started. Those 5 equations I showed you a little while ago are perfectly fine with that. If you say you start right here and end up down here, you don't have to say, by the way, I went up here and then I went down there. They don't care. They're built so they can say, just tell me where you started, where you finished. I'll figure out everything in between. So it's very powerful to just do this relatively simple thing of saying, here's this position, that position, you take the difference between the two and you get the displacement. And then in a moment here, we get the velocity is just the displacement over the time. So anyway, so we have this vector xo, which is the original velocity. We very often have an f on the final velocity, but it's also very common if it's the final velocity, just don't put a subscript there at all. There are positive and negatives of that, but this is more typical to do. And the one reason we do that is very often the original position will be 0, so you can just say x, and so that actually represents the entire displacement. Delta x is x final minus, in that case, 0, so x final is just x. Okay. So, alrighty. Now, what else? What's happening here next? And also, it's pointing out to you that if we wanted to know, for example, where its final position was, we could take its original position of, say, 60 plus its displacement of 100 to get its final position of 160. Likewise, you can do it the other way around. If the thing is zooming from here over to there, if you wanted to know the final position, you say the original position is 160 plus the final position, which is what? Minus 100. Notice that in this linear situation here, signs indicate direction. Okay? And remember we said that vectors have magnitude and direction, and the sign handles the direction. So it indicates it, but when you put it into the problem, it also takes care of the math. That's what I was saying about the divers and all that. Okay. And also have this delta x is x final. You might say minus x original, which is also means plus the negative of the original, which we'll see more about that when we're drawing these things. Okay, do we have anything else going on there? Oh yeah, one other thing here. Well, let's finish all these things off. So we have the average velocity, which I've already been talking about, and it is the displacement over the time, delta x over delta t. And if the velocity is constant, we can also just leave the bar off the top and just say v. And sometimes it'll be constant, sometimes it won't. And very often the original time, almost always the original time will be 0. So this term here will be 0. So we very often just have t underneath it. And I think that may be the way that equation might have been written down here. Yeah, over t. It's assuming that the original time was 0. All righty, where am I going here? Okay, and by the way, I think I may have mentioned this before, the slope of this graph will be negative over here, which matches up what we've been talking about. I hope I'm not running off and talking about things that aren't quite clear. I hope these are clear enough to you. I'm not trying to really go through all the nitty-gritty of all of them all the way through, so I hope that all makes sense to you. Okay, what I'm going to do now, let's see. Yeah, let's go ahead and do one of these example problems here. Okay, this is actually quite a simple problem. A car is located at x equals 160. Now, where the car actually is on our track here, the car is the location is where the mast is. For this car, I actually didn't do a very good job of saying exactly where the car is. You'd normally say it's like where one of the wheels is, or where the front of it is, or the middle of it, or whatever, because the car is kind of spread out into space in this universe anyway, or this part of the universe anyway. Okay, the car is located at 160. How long will it take it to reach a position of plus 150 if it's going at minus 15 meters per second? Is that all okay with you? It's at 160. Actually, I may have said minus there. How long does it take to reach plus 50? It's over here at 160. It goes over to 50, and it's going at a velocity, constant velocity of minus 15. We want to know how long it takes. That probably sounds okay. By the way, you've seen the little Kilroy here guy. Kilroy is always trying to figure out what's going on. He said, "Where are they going? Where are these people coming from?" Sorry. That's my special voice I shouldn't be using here. Okay, what do we have here? We're writing down what we know, what we want to know. The original position is plus 160, and we might as well let it do that. The final position is plus 50. And the average, or in this case we could say, actually I've said it's the constant velocity, so I don't need that average on there, is minus 15. That minus 15 doesn't mean it's going slower than 0. It means it's going 15 in the negative direction. The displacement is the change in position, and we know that the final position is 50, the original is 160, so we subtract it, and we get minus 110. And what we were trying to find out here was how long it would take, so we solve this equation for t, and we get delta x over v. Minus 110 over minus 15 give us 7.3 seconds. Now, what would it mean if we got minus 7.3 seconds? It would mean we did the problem wrong. As far as we know, well, there's fun stuff going on. People are also making a living off of negative time. The question of, is there negative time? As far as we know, and definitely when there are cars involved, there won't be negative time. I'll promise you that, at least for that'll be true at least for the next 15 minutes. Anyway, in our world, yeah, we don't have negative time. Time just doesn't appear to go backwards. Okay, all righty. Let's reenact this sucker, okay? It started out at 160. We can actually do this with our stuff. And so what I'm going to do is I'm going to, well, we have a marker there already. And it's going to end up over at 50. And so let's get this other marker to be at 50. And we want it to go 15. We have centimeters here, but all these, the numbers are just multiples of what the problem has in it. So everything actually should work okay. And now I'm going to go ahead and start it over here, because it really doesn't matter. We're just going to start looking at the motion when it gets to those crossing points. So I'm going to turn this on, and I'm going to say go. Whoops, that's not what I want to do. I want to make this minus 15. And let's get it to, okay, minus, yeah. All right, and we are finished with that. Okay, now let's see what's going on. Oh, I didn't let it go far enough, did I? I'm so sorry. Let's try that again. I was looking at the vertical lines, not the horizontal ones. That was close. Okay, all right. So here are our heights. Right here is our first point. So let's move our little time dealie over to there. And there's our final one there. And what we've done, we've set, well, it won't go over there. It's a silly thing. Let's see if this one will. Huh. Sorry about that. That's not supposed to do that. Okay, so we have our velocities correct. Here's our starting point at 160. Here's our finishing point here at 50. And so right here is the final time. Here's the original time, and that's a little over 10. And subtracting about, let's see, this is 3, about 2.7 or whatever. And we do end up getting our 7.3. If you'll subtract those two, if you'll measure them carefully, you'll find that it takes 7.3 seconds. So the equations are valid. They do what we're trying to get them to do. Okay, now I think let me just show you one more thing about this system, which I can't remember if you'll see these, but you may see these in the future. We have something up here called motion maps, and they do a similar sort of thing. I'm going to turn on the maps and turn on the motion and send the thing on its merry way. And what they do is to start drawing little dots on the screen. Okay. Well, those dots are pretty close. I'm going to turn that off and start back over. Those dots are awfully close together. Let's try this again. Okay. I don't know why that says 2.08. Okay. So what's going on here? Well, what's going on is we are seeing not just this, not this graphing business, but we're also seeing where the cart is at certain time intervals along here. And because these are uniformly spaced, we can see this thing has a constant velocity. So we have several ways of seeing this information. And by the way, these dots are made every 0.2 of a second. And so you could actually figure where positions are, displacements, and all that kind of business. There are a whole bunch of gadgets here, but those are a couple of the crucial ones that you'll be using along the way. I think that pretty well gets you going. Now, here's what's going to happen. Now that we finish this, and I think I covered it all okay enough, I'm going to come back and for the next video and give you a brief look at how to use the Velocity Lab, which is a lab done on the KET, the virtual lab site. No, excuse me, I'm sorry. It's done at WebAssign. So I'll go and visit WebAssign with you and see how to get all signed up there. You should actually, yeah. I'm trying to think. Yeah, I will have to tell you how to get set up there. You're already signed up. I'll have to show you how to log in and everything. And then you'll do the Velocity Lab there at the WebAssign site, and those will be graded online, very much like your homework is. So that's the next thing on the agenda. And then we'll come back and talk about acceleration, and that's where the plot really thickens. So that's the story on this for today, and good luck with it, and we'll see you next time.